And in the very early days of nuclear power, we tried lots of different types of technology. We tried thorium, we tried fast reactors, we tried metal fuels, we tried oxide fuels. We really went through a whole series of different types of technologies before the economics really pushed us down to thinking about essentially light water reactors mostly. However, we're now starting to rediscover some of those technologies that we were looking at some time ago, but we're doing that with very new materials and of course computer systems which are able to control reactor systems much more readily. So I think we are going back to, as it were, the future with fast reactors in particular, but with also alternative fuel types. So it's quite an exciting period of time for nuclear energy. Compared with 50 years ago, 40 years ago when we tried out those technologies, our understanding of the way that reactor systems behave, our understanding of the availability of new materials is significantly greater. And that's got to help those sorts of technologies looking forward. If we are at the horse and cart era, right, in terms of fusion, by the time my children are old, I find it difficult to believe the same technological leaps won't have occurred. I suspect it's a long road, okay, so I suspect it'll be 80, 100 years before it's economic. I think we might show that we can sustain reactions for significant periods of time well before that, but in terms of making it economic, that's a different thing, okay. One of the big problems is the erosion of the materials at the side. So you have the plasmas going round in some form of toroid or whatever the technology will be, and they erode the side materials at an astounding rate. So you have to remove that material somehow so that it doesn't pollute the plasma, so it doesn't get in the way of the plasma reaction. You've got to also remove the heat in some sort of efficient manner. So you need erosion resistant, high temperature resistant, corrosion resistant materials which will still breed the new tritium that you need whilst protecting the environment. The advantage of a fusion reaction is that it produces much less nuclear waste. Now, it's often said that fusion doesn't produce any nuclear waste, and of course that's not true at all. It produces a lot of activated products. So you will have nuclear waste, but it will be short-lived, at the most 1,000 years instead of much longer periods of time. So we will be able to deal with it, and it will produce an awful lot more kilowatts of electricity per ton of nuclear waste produced, probably 50 or 100 times more. So the nuclear waste won't go away, but it'll be much less of a problem. The other thing is that the sorts of materials used to produce the nuclear fuel, as it were, for those reactors, in particular things like lithium, are much more abundant, and you get an awful lot more energy per nuclear reaction in a fusion than you do with a fission reaction. So the fuel is more efficient in terms of the amount of electricity it produces. So those are the advantages. The disadvantages is that we haven't got it to work properly yet. Thorium has an advantage that you generate fewer of the long-lived minor actinides, including in that in plutonium. So the nuclear waste from thorium gives up its radiation, it decays away at a initially similar rate, but then much quicker after about 300 years, because there is less of these long-lived species. So from that point of view, it's an advantage. It's problematic because, of course, there is no fissile thorium isotope, which means that you can't just take the thorium, put it in a reactor and start the reactor and off it goes. You actually have to make uranium-233 from the thorium, and there's a step there, additional step you go through. So it's more expensive to use thorium technology. There are some other issues as well, surrounding, for example, the proliferation resistance of thorium. Again, thorium does produce less plutonium, so it's less proliferating of plutonium-based weapons technology, but it does produce, or you have to produce, uranium-233, which is a fissile isotope, which can be used to make some form of weapon. So again, as always with nuclear, there are swings and roundabouts, some positives and some negatives. I would argue that perhaps it's a transition from carbon through to fusion and renewables, but it could be that it's a much longer term process over many hundreds of years with some form of better use of the uranium resource, or perhaps even thorium resource, alongside renewables. And actually the relationship between renewables and nuclear energy is going to become very, very important indeed. So nuclear energy has been in a decline for a very long time, and a few years ago it started to pick up again, particularly in countries like China, but also in countries like Korea. Post Fukushima we seem to be in a situation of flux. So some countries are continuing with nuclear power, some countries are starting nuclear power, but a number of other countries like Germany, for example, seem to be stopping nuclear power. So it's all very uncertain at the moment. I think humanity is going to need all the technologies available to it. Whether or not, where the balance in the different technologies lies, I think will depend on the countries you're talking about. For some countries, nuclear will be a very small part of their energy mix, and probably not at all. I think other countries are going to be much more dependent on nuclear energy. I think France will continue to be much more dependent on nuclear energy. I think China will become more dependent on nuclear energy, so will Russia, as well as the other countries that we've been talking about. So it's going to depend. You know, only using 2% of the available energy out of the uranium seems to be very wasteful. So we need reprocessing from that point of view. We also need reprocessing from the point of view of reducing the burden of nuclear waste in terms of the volume. Okay, so it does that as well. Now, when the United States took the decision not to go down the path of reprocessing, I don't think that either of those two issues was as crucial as it is today. So I can see why, you know, as with so many technologies, the balance was not clear. So I'm a great believer that until we've really managed to solve the issues of what to do with nuclear waste, it's very difficult to persuade a population that we should invest in new nuclear. They can see that, or they hear about rather, the large piles of nuclear waste, I guess is what's in the mind of many people. And they don't want to see us accumulate more nuclear waste without knowing how to deal with the nuclear waste that we've got. Now, in fact, new nuclear technologies will produce a lot less additional waste per kilowatt of energy generated. So we need to explain that. But at the end of the day, we have to dispose of our nuclear waste. Technologically, we can do that. We can reprocess, we can turn a lot of the nuclear waste into glass blocks, which are much more concentrated nuclear waste, so you're reducing the volume, you're not reducing the amount of nuclear activity, but you are reducing the volume. We can also dispose of spent fuel directly, so there are numbers of technologies which we can use to do this, but they have to be demonstrated. And what we failed to do is really demonstrate it to enough of the world's population. And so it remains a priority. But I think it's a technologically solvable issue, without question. The most feasible way of dealing with nuclear waste at the moment is geological disposal. Absolutely clear. But geological disposal is not really one technology. It's a whole set of different types of technologies, because the different rocks that you would use for that geological disposal mean very different things for the way that the chemistry of that environment interacts with the nuclear waste, the way that the water that moves through the rocks will interact with that nuclear waste. So I don't think it's really that it's one technology. But perhaps looking a little bit more out of the box, then you have things like deep borehole technologies. So instead of going 500 meters underground or 300 meters underground, which is a geological disposal, typical geological disposal depth, we're talking 3 kilometers down. And you just have a very long borehole and you put the waste right at the bottom of that. So it's so far away from the biosphere that actually even on geological time periods of rock being eroded or things like that, it's never going to reach the surface for millions and millions and millions of years. So that's one particular technology. But There is also the recycling not only of the uranium and the plutonium, but the minor actinides, and then getting the nuclear waste back through rate processing to a sort of state that 300 years' time the radioactivity, residual radioactivity, is very, very small. So that's kind of another completely different way of dealing with it. I believe very strongly that Germany made the decision to remove themselves from nuclear energy, very much from a point of view of a population's lack of understanding, frankly. It was a political decision, it was not a technological decision. The people talking to the German government at the time knew very well about the use of nuclear energy, but the population has always been relatively anti-nuclear energy for sort of historical reasons, and at that point I think the German government had to do something popular. I genuinely think that's true. I do not believe that they made it for a technological reason. Now, people will disagree with me, I think, strongly on that one, but that's what I believe. Now, France took a very clear decision to go with a lot of nuclear energy. Now, recently they've been reviewing that, and they may reduce their dependence on nuclear energy to a certain amount. But they didn't have a lot of coal, they didn't have any oil, they didn't have very much gas at all. So for France, the initial decision on nuclear was due to what resources that they had to hand, and the real wish to become independent from an energy point of view. And actually it served them very, very well indeed for many decades. And I think it will continue to do that going forward over many decades. I think nuclear power has an outstandingly good track record in terms of its safety. But that's the sort of thing that involves the questions of human use of nuclear power, human intervention in the systems, and how those systems are set up. So it's a really complicated issue. So Fukushima has had an impact. Now, I find that, on the one hand, not surprising, because there was an issue, there was a release of radioactive material. But on the other hand, I find it surprising because no single person lost their life as a consequence of the nuclear disaster in Japan, but numbers of people, many thousands of people, very tragically and sadly lost their lives due to the natural processes that were going on. So to a certain extent, I would argue that Fukushima showed how vigilant we must be in thinking about old designs of reactors, in considering turning old reactors off and not being frightened to do that. But at the same time, it showed us that even a 1960s designed reactor that was at the very end of its lifetime, it was, even in the worst natural circumstances, was not in fact an environmental disaster. It was a local disaster. So I think if you can't explain a technology simply, then you probably don't understand it well enough. I mean, I know that sounds trite, but honestly, I think there's a lot of truth to that. I really do. People are generally much more intelligent than we sometimes give the general population credit for. I think through television in particular, I think through websites, by discussions, I think it's just a general continuation of the sort of things that you're trying to do here. Just talk about things and get challenged about things. Discuss the less comfortable questions, okay? And continue to talk about these things. So that and engage people. My personal opinion is that every time you carry out nuclear work, whether it be towards energy, disposal, generation, operation, you are educating a population to be able to deal with nuclear issues. So there is, to some educational degree, a concern over proliferation. So in your education of people to engage with nuclear energy, you I think, is beholden to discuss the issues of proliferation. If you go back 150 years, then the really exciting lectures that were given during Victorian times were on science and technology. People thought these were wonderful things to go and see. And we've got some great people who go out and give these sorts of lectures. And I'd like to see lots and lots more discussion on energy and other resources like water and where we're going to get that from, which I think is also a very difficult issue. I think we need to stop being frightened about thinking of different types of technologies. Of course, from a policymaker's point of view, the danger there is that you don't ever make a decision, or you cloud the issue. So coming back to the public acceptance, we need to allow the public to understand, or aid the public to understand, that there are lots of different solutions, and it doesn't mean that a particular solution is necessarily better or worse than another one. It's just that it might be more economic, or it might be more feasible in the geology that the country has, or it might be that at this point in time we would prefer to use one than the other. So there isn't a silver bullet, I guess, is a way of saying that. It is really important for scientists never ever to tell people what to think. Okay, it's not our job to say you should think this. It is a job to say these are the facts. This is how I see the thing. This is what I am sponsored by Westinghouse, or I'm sponsored by whatever, and admit that up front. But then try and explain the science. But trying to tell people what to think, I think, is wrong, and not only wrong, it's counterproductive. My name is Robin Grimes. I'm Professor of Materials Physics and Director of the Centre for Nuclear Engineering at Imperial College.